Hi everyone. So I think maybe we can start now. We're ready to start? Okay, perfect. So hi everyone. I hope you're having a great time today at the conference. That you're enjoying Dubai. My name is Clément and I'm a Solidity developer. And today we are going to be talking about how we can punch contracts in the face, how we can break contracts, how we can test them, and maybe if we are lucky, how we can catch some bugs. So we are going to start with the basics. And when we are thinking about smart contract development, I guess there is like this picture, this flow chart that we can picture in our head. I think most of the good developers have this flow chart coming, all this life cycle for smart contract. Obviously, you can skip some steps, but only if you're pure degen and you want to ship unaudited, untested code, which I wouldn't recommend, to be honest. But yeah, basically the idea is that first you will be speccing your smart contract. You will be just defining the purpose of the contract. Once you're ready with the specs, then you can start the development phase. And then during the development phase, you can be right at the start, or once you reach like a specific milestone, when you're happy with the state of your contract, you can start writing tests. Maybe it can be by the end of the development cycle. Everyone has different thoughts about it, but anyway, you should be testing what you are doing. At some point, maybe no one is perfect. Bugs can be in there. Obviously, if you found bugs, you will want to fix them. So you can go back to the development phase. You will fix the bugs, testing again. And at some point, you will be ready. And then you can deploy, or at least go to the auditing phase, which should be what most people should do. But yeah, this is more or less what's happening. But you will tell me, okay, we have maybe bugs. How do we know if we have bugs? How we can test our contracts? So that's obviously the main topic here. And when it comes to smart contracts development and testing, there are a few different techniques that we can use. Some of them are very basic. Some of them are a bit more complex, and we're going to talk about them right now. So this is a very simple contract. This is just like, I'm sure many of you are familiar with it. When you're making a new Foundry project, this is like the example contract. It's very simple. You're just like, you have like one variable called number to store a value, and then you have increment, so it can be used to increment the value and then set number, so you can just set the number. So very, very simple. How can we test these contracts? Well, the first thing that you can use, the first technique is unit testing. So basically, unit testing is very, very simple. You have inputs that you will provide to the test, and there is like outputs, an outcome that you are expecting. So in that case, we want to test the increment function. What are we going to do? We're just going to call it. It's very simple. And we know that the increment function will increment the value. It will just like add 1 to the value. In that case, we start with 0. So if we increment our number, it will be 1. So unit tests are very basic. They're very simple. They don't do much. They just do actually the scope you're giving to them. And they are not going to be like trying to go further. And also, the state is not persistent, which means that if you run this test, it will be always the same state at the end, because it's the same state at the start. Which is why, in that case, the value will be always 1, because we start from 0. Then we have something called stateless fuzzing, also called just like fuzzing in a more general way. So in that case, fuzz tests are a bit more advanced. They are a bit more complex, because They will also start with some inputs, but in that case, they are not expecting inputs from you. They are just going to use random values. So what's happening is that here we want to test our other function called setNumber. setNumber requires an input, uint 256 in that case, and well, we want to try out this function. We want to know if by providing a variable to setNumber, it will store it in the storage. Obviously, there is like a huge amount of different variables that we can pass to this function. So we are not going to do it by hand, otherwise it will take us like 10 years. But we are just going to give the possibility here in this case to Foundry to use like a random value, so it will be x. And Foundry will know that it can just like generate a specific value for x, can be 0, 1, 2, 3, or whatever, like a huge number, and it will feed it to the setNumber function. So a few things that we have to keep in mind here. I've been talking about random values. It's true, but it's more like something you still have control over, because you can still say, I want random values, but I don't want 0. I want random values, but I want above, I don't know, like 1 million, something like that. You still have control over that. And even if this test will be running many times, this is what is called runs in Foundry or fuzz testing in general. Maybe you can set up like 32 times. So this test will be running 32 times, but the state won't be persistent. Every time we will start from the base state, so what you defined in the setup function. And then we have stateless fuzzing, aka invariant testing. So in that case, things are a bit different, because we are not providing exactly an input, we are not providing exactly an output or an outcome, but rather we want to test, we want to check an invariant. So I guess the next question is, what is an invariant? Well, if we just take the definition, invariant is a property which remains unchanged when a specified transformation is applied. So this might be a bit obscure, but basically just that you have a statement, and this statement must be true, must stay true, even if many things are going to happen. So what is going to happen from like a technical point of view is that you will write your invariant. So for example, this is true and it should be always true. And then in our case, Foundry, for example, it's just going to fuzz the hell out of the contract. It's just going to call a bunch of random functions, and the goal, Foundry, its goal would be just to break the invariant by trying many different paths, trying many different function calls to see if there's a way to break this invariant. So I'm just going to give you like some real-world examples of invariants. So something very simple with the, for example, ERC20 tokens. The total supply must be the sum of all holder balances. So if we have 1,000 holders and they have all 1 token, then the total supplies may be 1,000. This is something very simple, but this is an invariant. Obviously, in that case, this seems obvious, simple, and it's quite easy to test, but we can go to more complex things. If we take the case of the wrapped ETH contract, then we have the ETH balance held in the wrapped ETH contract must be equal or greater than the total supply of wrapped ETH. This means that we can be sure that if we have wrapped ETH, we can always redeem, we can always unwrap and get some ETH. So this is for the solvability of wrapped ETH. Once again, this is invariant. That is quite straightforward to test, but still quite interesting to set up. And then we have xy equals k. So you know this, for example, from Uniswap pools. In that case, they are using that in their pools for the swaps to validate if a swap can be done or not, and just that the reserve of tokens x times the reserve of token y equals their invariant. So we can sum up this this way. Basically, we have unit and fuzz tests. So they are kind of similar in a sense, and they're very good to test very specific things. For example, you are going to write some functions for a library that is computing the square root of something, and you know that, for example, you have a bunch of values that you will feed on one end, and on the other hand, you know that the outcome, the return values should be this A, B, C, D, etc. So unit tests, fuzz tests, they're very good at testing very specific things. And invariant tests, they are more used for global testing. Let's say you have like a brand new lending protocol, or you have like an AMM. So you might want to use invariant testing to check if some properties would be always true. It can be also done for something simpler, like, as I said, like ERC20. But this is the idea. Here, in that case, you might want to use invariant testing. And yeah, for example, you have a new AMM, and you want to be sure that if 100 users come and they are going to buy, sell many times, well, things will be fine in your contract. Nothing is going to break. I don't know, like some value is not going to overflow, or someone is not going to be able to redeem the liquidity they provided, things like that. And you can do that with invariant testing. With the other tests, like unit tests, it will be way more complicated to simulate specific scenarios like this. So now you might be wondering, okay, this is cool, but how can I actually like write invariant tests? Well, the good news is that we have many tools. We have the amazing Echidna. So the logo is not very good quality, but the tool is very powerful. It's from Trail of Bits. They made this tool like a long time ago, maybe more than 5 years, I think. So it's kind of an OG tool. It's using Slicer, another tool they made to do like static analysis. And Echidna is very powerful. They use it for most of their audits. And they've been able to use it to find bugs in protocols such as Balancer, Uniswap, even in DAI. So very powerful tool. You might, the learning curve might be a bit steep, but it's a very nice tool. Trail of Bits also released Medusa, so I haven't tried it yet, but basically I have some notes here. It's written in Go, based on Geth. You can do parallel fuzzing, smart mutational value generation, whatever that is. I'm not sure, to be honest. On-chain fuzzing, enhanced debugging capabilities. So looks very good. I haven't tried it yet, but it's on my to-do list. Then you have Halmos, which is quite new also. Maybe it was released, I think, like one year ago. In this case, this one is more for formal verification, and it's also using like symbolic testing. So in that case, symbolic testing is a bit different because it will use like math formulas. So the goal is more that you have your invariant that can be translated to math, basically, to formula. And then what's happening is that using that formula, you can convert it back to code and find a way to break your contract through all this mathematical representation of your invariant and your protocol. And then obviously, I feel like the most obvious choice nowadays is Foundry, because Foundry has so many things, so many tools. They have like a very powerful testing framework, which is also including the invariant testing. It used to be good, but a bit basic, but now they have very good features. I don't know if it's like as good as Echidna, but they have many things super interesting, like shrunk, replay, stuff like that. Basically, once the Foundry has found a way to break your contract, it will try to shrink the whole path. So how many functions were called to break your contract? Maybe at first it was 100, then Foundry will replay this attack, replay this scenario, and it will try to find the shortest way to break your contract. So it's extremely powerful to debug stuff. So let's get into business, I should say, and we are going to see how we can actually set up some invariant tests on a more like low level. So basically, we have like 3 different types that we can use. The first one is the direct assertion. So it's very basic. You just have, I don't know, like 2 values in your protocol, and you want to compare them. You want to be sure that this assertion, this invariant, is always true. For example, in that case, we have the token, the total assets should be greater than or equal to the total supply. So you can just write this, and then Foundry will like call a bunch of functions from your contract, and at the end maybe it will call like 1,000 functions, and at the end it will check if this is still holding. So very simple. The second one is the ghost variable technique. So I like that one because that one basically is having a way to track variables in your test files, in your test contracts, and then you will compare them to the actual values inside of your protocol. So a very simple example would be, we are going to do like transfers in an ERC20 contract. So what's going to happen is that obviously the balance of a holder will be increasing or decreasing in the ERC20 token contract, but I can also track that in my test contract. And what's happening is that I will have 2 values, one that will be in the test file and the other one in the actual token contract. And at the end of the run, then this invariant can also be checked. The last one is de-optimizing. This one is pretty fun, actually. Let's say you wrote like a very, very, very good and very gas efficient, very performant, very optimized algorithm that you're using to distribute rewards in real time to many users, like, I don't know, for yield farming or something like that. How can you be sure that, well, your formula is correct, or how can you be sure that your implementation is correct? Then you can do the naive implementation technique. Basically, you're going to write a very, very simple, very naive implementation of your code inside of your test file. You don't care about gas, you don't care about anything. You can use for loops, whatever you want, because you're just like testing, so it's completely fine. And what's going to happen in that case is that you will be comparing once again the value that is that was computed inside of your test file against the value that was computed inside of your protocol. So this can be used, let's say, for example, you have like an AMM and people are like providing liquidity, and you want to be sure that they are earning fees, and they should be earning fees this way. So maybe you have a very optimized algorithm inside of the pool contract, but in your test you can just, for example, have a very naive implementation that will use like mappings, for loops, stuff like that. So it's like an interesting way to compare things. So an example, so this one is taken from the wrapped ETH example invariant testing repo from Horse Facts. And basically, we have like here 2 very simple invariants. So the first one is conservation of ETH. So basically, we are just checking that the supply of ETH is just like equals to the total supply inside of the wrapped ETH contract. And there is another one that is using what I've been talking about, the ghost variables. I mean, in that case, we are just checking that the balance of ETH is like the sum of what was deposited by the users minus what was withdrawn by the users. So you can see like invariants are quite simple. They are just like things that you want to check in your contract to be sure that the contract is working the expected way. But the hardest part is now, and is how can we check the actual invariant? Like, how do I need to write? Like, how can I write a test for this? Well, you have this first, how can I say? It's not even a technique, it's just like the open open technique, open way. You just say, okay, I have this invariance, and then Foundry, you just figure it out. The likeliness to find something here, like a bug, I mean, is very low because Foundry is just going to call random contracts. It's just going to call random functions with random values, and you won't be sure exactly what it's doing under the hood. I mean, you can still track it, but you cannot really control it. And the thing is that Foundry doesn't know, like, if you want to swap something, it doesn't know, like, exactly which, I don't know, like, amounts it should provide. It doesn't have, like, maybe the right token balance, things like that. So we have to go we have to use, another method called the handler method. So basically, it's very simple. We are using, like, 3 elements: the handler, the targets, and the invariance. So you guys already know what are the invariants. For example, as I said, total supply of wrapped ETH or total supply of a token. And then we have the targets. Obviously, this is very basic. This is very simple. Targets are just our contracts. We want to try our protocol. So we are going to say to Foundry, for example, you are only going to call our contract. This is like the ERC20 contract or whatever, or our AMM. And we can also go a bit further, and we can say you want only to call this function or that function. And then we have the handler, and the handler basically is kind of a helper contract. We're going to see that in a minute. And the handler, is helping Foundry into, like, calling the actual functions. As I said, if you are making like a brand new AMM, then Foundry doesn't know how to make, like, a swap. So you will have to help him out here. So what is going to happen in that case using the handler method is that we have Foundry, and Foundry is going to call the method here from our handler. And what are we going to do is that we are going to say the targets or actually the functions from the handlers. So Foundry is going to call these functions, and then our handler is going to call the different contracts from our protocol. So it's going to do that 1,000 times, for example, and then it's just going to check the invariant at the end. So from, like, a very code perspective, how does it look? Well, you can have, for example, this handler. This is also taken from the Horsefacts repo. You have some ghost variables. For example, you want to be sure that when people are depositing or withdrawing, you want to track how much was deposited or withdrawn from the wrapped ETH contract. So you can have, like, ghost variables there. And what is going to happen also in that case, it's a bit advanced topic, but you want to be sure that the callers are not, like, all the time the same address, because it wouldn't make sense. For example, if you're making an AMM, you know that many wallets will interact with your contract. So what is going to happen here, we are going to use, like, a setup that is doing, like, what is called actors, and basically we can create or use actors. Let's say, for example, Foundry is going to make a new call, then we can say, okay, for this new call, you want to call the deposit function. Okay, so let's create a new actor. Maybe we are going to give to that actor, like, 1 ETH, and then this address can deposit or try to deposit 1 ETH. But it's also the case for other functions. For example, we can say, okay, we want to withdraw. So you have, like, different scenarios. For example, you can say this address wants to withdraw. Maybe it's an old actor, so he's already holding wrapped ETH, so he will be able to withdraw, but maybe he's not holding anything. So maybe we want to check that if an address that is not holding wrapped ETH, is he able to withdraw ETH at the end? It's not possible. So this is also interesting because with invariant testing, we have different ways to set up things, and you can have invariants that should fail, or at least revert, or some that should not revert. For example, if you're making an AMM, or even in that case, do you want to make the test fail if someone is trying to withdraw more money that they deposited? Maybe not, but you just want to be sure that at least the transaction is reverting, but the test is passing. And then these are the actions that are defined into our handler. So basically you have the, for example, deposit function. So this is also a function that is in the wrapped ETH contract, or at least an action that you are supposed to do. And what is going to happen here is that you can see like the you win 256 amount. So we can also provide like a random amount here, obviously. And you can see like the create actor modifier. So this means that we want to create a new actor, and we want to we want to give him some ETH so they can deposit some ETH inside of the contract. And for example, we are also like increasing the ghost variable deposit sum. So in the handler, everything will be like all the logic you want to check, like the ghost variables, the actors management will happen in this contract. And if you look at the withdraw function, what's going to happen here that we still have the random amount parameter, but we also have the actor seed. It's just a way for us to say, okay, let's just use like a random actor from all the actors we created. And then once again, we're just like updating the ghost variables. And obviously we are calling the actual wrapped ETH contract. In deposit, we were depositing, and then in withdraw, we are withdrawing. So once you have the handler done, then you can go back to the setup. So I showed you this earlier. You have like, in the actual test file, you have like your invariants, but then you might want to update at some point. It's here. You might want at some point to update the whole like test file. And in this case, we just want to say, okay, so in the setup function, so we are starting with like a clean state. We deploy the new wrapped ETH contract. We deploy the new handler. We give the address of the wrapped ETH contract to our handler. And then what is going to happen is that we have this weird array of bytes for, it's like function selectors. And this is telling Foundry, we want to call all these functions from our handler contracts. And at the end, the last two functions are actually quite interesting. You have like target selector, and this is, well, what I just described. We say only call these functions from the handler, and then we can add the target contract and say only call this contract. If you don't do this, maybe there's a chance that Foundry will try to call another random contract just to see if the invariant is still standing. Obviously, will be standing because your contract won't be interacted with. And so this is another screenshot from another project I'm working on. But basically, once you've been like running your invariant, you can see like we have the here number of runs. So we call the invariant test call invariant tracks total tokens sold and proceeds, etc., whatever it's called. We have 32 runs, which means that the whole thing was has been running like 32 times, and there is like 16K calls. So this means like 16K functions were called randomly, and there is also the amount of function calls that reverted. In that case, we don't really care about reverting, because what we wanted to check was actually like that in that case that we were tracking properly the amount of tokens that were sold. So someone buying, we don't really care if it's failing. And you can see like this report generated by Foundry. You can track the amount of calls that were successful, that reverted, etc. So yeah, I guess this was the introduction, but if you want to go further, I recommend you like a few different very interesting resources. There is this article by Rare Skills, pretty interesting. Then obviously you can check the GOAT, Patrick Collins. He made like many videos on YouTube about testing, invariant testing, many interesting things like that. Another GOAT, Horse Facts, he made a cool presentation at ETC, so the video is on YouTube, you can check it out. And then there is also that one video from Trail of Bits. It's actually not one video, but I think 10, so you have like 10 hours of tutorial how to use Echidna. It's pretty dense, but very interesting. Good examples, Sablier V2, Flow, Doppler, my own contract. And Uniswap before, Echidna wrote, the Trail of Bits used Echidna to write very good invariant test for V4. And something very interesting that you can also read, this is the list of all the bugs that were caught using Echidna. So this list is obviously by Trail of Bits, but they have like 20 reports. And yeah, you can read this out, it's very interesting. And this was the last slide. I forgot to make a slide to thank you guys for listening to this talk, but I'm done. Thank you very much. Any questions? All right, thank you guys, have a good day.